So this is the beginning of our discussions of spectroscopy, and I'm going to go through each one independently. So for this, you want to print out this packet of notes, and you also need a highlighter for this discussion because I'm going to highlight what you need to keep track of. So in our unit of spectroscopy, we're going to look at three different kinds of spectroscopy. One is IR, one is mass spec, one is NMR. So IR is our first step in the process. So it is abbreviated IR. It is looking at infrared spectroscopy, and that is why we spent some time talking about the electromagnetic spectrum. So what we're getting at here is, if I get a molecular formula C4H9O, okay, what is that molecule? Okay, so as we talked about with degrees of unsaturation, we could do that formula and see if I have any double bonds or anything in that structure. But what we're going to use this IR spectroscopy is to identify functional group. And that's really what IR is used for currently. It used to be the premier spectroscopy, but now NMR has kind of taken over. So this is really only used to identify functional groups. And as we go through spectroscopy, what I want you to think about is pieces of a puzzle. So infrared is going to give us a piece of the puzzle to tell us what functional group do we have. So really the basics of this is infrared spectroscopy deals with the interaction of infrared light with matter. Okay, so if we take a sample and we hit it with infrared light, what happens to it? So we have a relationship from Planck. Energy is equal to Planck's constant times the frequency of the light. And we know that the speed of light is equal to our wavelength times our frequency. So that is why we did those beginning calculations as we did them. So in our study of IR, we are going to also be exposed to something called a wave number, okay? So wave number is a weird looking V with a bar over it. And so you're going to use that as a unit. It is what we call the reciprocal of the wavelength, So that means 1 over wavelength. And since wavelength is in meters, this is an inverse meter. But what you're going to see on IRs is they are going to be inverse centimeters, okay? So how this works is molecules are what we call flexible, okay? And they are a collection, of course, of atoms, all right? So because these molecules are constantly moving, our bond lengths and bond angles are continuously changing due to a vibration in the molecules. So again, think of kinetic energy, everything is moving except when we're at absolute zero. So therefore, I have a vibration in a molecule. If a molecule absorbs infrared radiation, okay, the vibration produces an isolating electric field with the same frequency as the frequency of that light. So what scientists figured out pretty early on was that there was some kind of pattern. So if I hit an IR light into a double bond, or if I hit IR light into a ketone, there were specific things that it did. So think of our carbon-to-carbon bond, okay? That the longest carbon-to-carbon bond is going to be your single bond, and then the shortest bond is going to be your triple bond. So depending upon what type of bond that you have in there, it's going to behave differently. So flip to the next page. What this goes into, just to kind of give you a list of flavor for the theory behind this, you have two different kinds of what they call vibrations in the molecule. One kind of vibration is called a stretch, okay, which changes what we call the bond length. So again, think of a single bond, double bond, so on and so forth. So what this picture is showing you is, again, that you can stretch a bond or you can compress a bond. So that is one type of thing that you can, the vibrations of the molecules can do depending upon what frequency you hit it with. A second type of vibration is called a bend. This changes what we call the bond angle. So sometimes scientists call it scissoring, rocking, wigwag. There's actually scientists who say things like that. Realize that if this is your normal bond angle, okay, you can compress it or you can widen that bond angle. So please note, and you do have different kinds of vibrations. You could have symmetrical or asymmetrical, depending upon if you're within the plane or outside the plane of where the bond is. But do note that the stretching motions are going to require much more than just the bending, which makes logical sense in terms of you changing a bond and stretching it out rather than just kind of bending it a little bit. So go to the next page. So a molecule will always absorb a unique set of IR frequencies, okay? So IR spectrum is often like in a fingerprint. So again, emission spectra, that's a fingerprint for an atom. IR is a fingerprint for organic molecules. So a little bit towards the middle of this paragraph, any individual bond in an organic molecule with symmetric structures and identical groups at each end of the bond will not absorb the IR range. So what that means is once we have a molecule, like they go through an example here of ethane, the bond between carbon and carbon does not absorb IR because there's a methyl group at each end of the bond. CH bonds with the methyl group do absorb. So it depends upon what actual bond you have in order to see if you have an IRP. So go down a little bit more here. An IR spectrum is for the entire molecule, but we're just going to use a section of it. Again, we're just going to focus on, can it give me a functional group? And then we're going to use something called NMR to give us more of the structure. So just to give you just to sum it up here, the fingerprint region and a functional group region. So this is what we call an IR spectrum. Now do realize on the bottom here, this is wave number, and it goes from right to left. Okay, so it's kind of a little different than us going from left to right. And over here on your y-axis is percent transmittance, so how much light goes through there. So we are going to focus on what we call the functional group region. Okay, that's what we're going to focus on. So we're going to focus on everything above probably 1,000 wave numbers and all the way up to 4,000. So we're not going to look at what we call the fingerprint region. The fingerprint region is unique to the molecule. Functional group is similar for molecules with the same functional groups. So you're going to see the same pattern if you have an alcohol, or if you have a ketone, or if you have an aldehyde. What's going to be unique is in the fingerprint region, what you see there. Okay.